Hi, my name is Elizaveta Goncharova, and I am from AIRI institutions, and today I would like to present a report together with our colleagues in Fusion Brain, which will bring us to the world of amazing LLMs, and we will try to understand in the presentations as to how it happened that despite the very simple tasks those LLMs are trained, they are so much capable to solve some applied tasks so well, the tasks we are facing every day. So before starting, I would like to look at the history and LLPs and LLMs as virtual assistants. Well, you can see here that the development started mid of last century, but the approaches at the time mostly were based on the rules related to formal grammar rules and regular expressions. But then further on, neural network approaches to process the natural languages, and as we can see, transformer models came to the forefront, and all those bigger examples, very successful examples, are linked to the architecture of transformers. The transformer architecture, well, not very simple either. You have to take the decoder, encoder, and to match them, how many parameters you should train your model in, and at which spot you have to add the layer north. And for all those development years, the survey was done, and in 2017 there was a big paper written on that. And we can see now that we can answer at least one question here as to the more parameters the model has, and the more high-quality data set was used to train, the bigger spectrum of tasks the model can solve, the more smarter it is, as we can put it this way. However, despite the fact that we can see that the scaling, of course, impacts the qualities, we cannot answer the question as to which information the model stores in the training ways. What does it know about the world? What linguistic knowledge it can encode in the weights we gave to it? And seemingly the answer to those questions will open up more opportunities in processing natural languages if we understand how to train the model in the right way, what it knows, and how you can interpret the results. So totally this question generates more questions, still more questions, how to assess those LLMs. Mostly here we remember the word benchmarks, and that's indeed true, because benchmarks are specially made up tasks in different fields of knowledge, using which we in some way can unify in a unified form to assess the quality of LLMs. On this slide I showed only two, the most vivid examples of benchmarks, Big Bench dataset and datasets with exam questions, MMLU. Well, generally, if you look at the graphs of the results of those models on Big Bench dataset, we can see that indeed scaling does impact. The more parameters the model has, the bigger quality the result. The MMLU, well, it's curious because it was offered several years ago, but the maximally good results were taken now in 2023. And we obtained, which doesn't correspond very much to the predictions that had been given by the authors for the quality of the model on average in time. And we can see here that despite the fact that the predicted quality was about 63.4% average for the whole data set, in 2023 the GPT-4 model allowed us to achieve the quality of more than 86% for for all exams included into the data set, which generally is closer to the human level of solving such tasks, which is quite a curious result, which says that the models are becoming smarter, the parameters are becoming more in number, but seemingly there are some characteristics that still can impact the end result. And in addition to the existing benchmarks, we can note that with the big number of parameters and more complicated procedure of training the model, they are acquiring new capabilities, even those they were not trained in. For instance, we can see the language transfer, which can happen for LLMs when training in one language. Suddenly, the model asks, well, in another language, and it can write the program code, not being trained specifically for this task, and even with some small adaptation to the new output, the model is capable of perceiving new modalities as an input. Besides answering questions on the text, the model becomes capable of answering questions by images or even to describe audio tapes, audio messages. So this domain opens up new opportunities in working in LLMs. So we've looked at the procedure of assessment, and we could see that we can quite objectively understand which model is better, which is worse, and which knowledge from which domain are represented better or worse. Still, a question of benchmark assessment not yet opens up well enough as to what the model knows exactly about the world, about the language, and what is stored in those weights of the models that we mentioned at the beginning. So, this is the field that assesses how well the models store information about the world, what knowledge they have in their parameters, and it is solved using another approach based on the linear probing, which is quite a very interesting methodology of knowledge assessment inside the model, which is done in the following way. Let's, for instance, take a very simple linear model of classification or linear regression. For instance, at a task to be solved, the model should know a certain part of information about the syntax, or, for instance, about the location of an object, and some part of the knowledge. And we'll try to calculate the images of each layer of the model, and let's take it as input and train it just in a simple way and look at to which quality will be the best one in solving such tasks with certain knowledge available. So this approach was provided a long time ago, but it is actively being developed and applied now to assess LLMs and to understand what exactly the model knows. As an example, I can bring you several interesting works, in one of which the authors suggested to review the global map the model can makes up, and interestingly turned out that actually different parts of big modern LLMs are activated at the information of different locations of objects and different time of events. That this or that event occurs. And as a visual example, the authors even built up certain clusters of activation inside the model to show that those clusters are well distributed by the map of our world, which is quite a curious result. Then next work provided even further step. They decided to see how well the model understands the factology and knows the information about the world. Well, they decided to do it in the following way. They suggested a benchmark head to tail, and this benchmark has to predict, the model has to predict relations between the substance and the facts available here in the world. The authors interestingly found out that the modern models are more successful, or stronger models models,
which was ChatGPT and Llama. They turned out not to be the most successful in trying to solve this particular problem, and in the majority of cases the model is unable to correctly predict the link between the essence and fact, which overall tells us that the question of how one should define the facts and what is the graph of knowledge that is contained within the model is a bit of a difficult issue, the answer to which is not as trivial as it may seem to be in the first place. Now, to continue this study, this survey, our group went into the linear probing of the model from two other perspectives. In the first place, we were interested to understand what kind of linguistic knowledge can be found inside a model. What information about the language structure the model may encrypt inside its internal notions. The second question that was interesting to work on was coding different concepts from other modalities. For example, we know that we have a language model. It was trained upon the big core of textual data, but the recent work, including the one that we are working on in our team, points to a simple training of a small tier of adapters, making it possible for the model to understand the entry points from other modality, like images. Now, interesting thing is that the main information about the visual concept is hidden inside the language model itself, or it is us who bring in this information via training these adapter layers. So, raising these two questions, we decided to launch two additional research. It's no secret that our language is organized hierarchically. We can operate in terms of the sounds, phonetics, words and forms, morphology, or word meanings like semantics, as well as more complex structures, higher tier structure like discourse and pragmatics. This is when we operate not within one word, but throughout the whole body of text and even the body of the whole language. So, overall, different studies which would analyze linguistic knowledge existing in the models, they took place a long time ago, and the authors primarily were researching encoding models and encoder architectures. And in their past results, they arrived at the very same conclusion that overall the morphology, syntaxes, and semantics can be coded by the model quite well. But the discourse and pragmatics are not so well represented, particularly inside the model with 7 million parameters, which is quite a complex linguistic structure, difficult to detect. And so, in our study, we wanted to experiment with the new modern language models, and first of all, try and take a look at how well they can code this information, and secondly, to what extent the size of the model can strongly affect the quality of the discourse encoding. And so, what we saw and basically brought us to several interesting takeaways. First of all, the size of the model indeed matters. The models with a bigger number of parameters, like, for example, MPT-7B, shows a better quality compared to all the rest of the smaller size models. The second interesting thing was that the most representative layers and decoders are in the middle of the models, and here you can see that for decoders on the left chart, there is a very dramatic spike towards the central layers and the decline towards the lost layers, which may be explained by the fact that the information about linguistics and facts is encoded in the middle layers, and after that the model is trying to shape itself up to suit the ultimate purpose and the results, language modeling. And the third interesting fact is, despite the fact that the bigger size decoder demonstrated better quality. Very small decoder Bert and Roberta demonstrated a better outcome, like, for example, predicting discourse links inside a single sentence compared to other bigger size architecture. So, in this sense, in terms of the vector linguistic representation, encoders quite often work better than decoders, irrespective of the size of the model that we're trying to train. The next experiment that we conducted was related to multimodal studies. As I mentioned, it was interesting to see to what extent the text models were being well trained only upon the cores of text, were able to encode information specific for the new modality. For example, we have a color. Color is a visual modality, and we have shapes, which is also a visual line of recognition. And in order to understand how well these notions, are encoded within the language models, we took two ones, which is Quen LM with 7 billion parameters, the language model, Quen language model, and multi-model, the Quen visual language. And we ran a number of experiments which helped one to define whether information about shape and color is somehow encoded inside a model, and within which model, language only or multimodal one, this information is better represented. So, some results I am showing on the slide to depict what we have discovered. For example, to encode color, you can see that the vector representation of different colors turned out to be very close in as far as cosine similarity with other colors. Like, for example, purple was closest to the blue, dark blue, which is quite rational, but also very close to an orange one, which is unexpected. This is within the Quen language model. The same applies to the shapes. Oval shape closer to the pentagram, which is not very logical, but within the language model, that seems to be more proper. Now let's take a look at the kind of difference we were able to discern once we looked at the vector representation achieved with the help of multimodal architecture. Quen visual language model was trained apart from the text modality using data from pictorials and input text. It was logical to expect that this model would be a bit better in coding the notions related to the visual modality. Overall, it turned out to be exactly that way. Intuitively, it seems that the purple color should be closer to the red and blue because it is a result of mixing the two of them. And in the case of the multimodal Quen, that has been confirmed. Respective embedding, which complies with the text which encoded the purple color by tokens, ended up being close to the embedding of the blue and red, and then way more farther away from the origin yellow and green. So we see that the embedding words and respective texts which are linked to oval shape are closer to the rectangular shape rather than pentagram, although the pentagram is not very much far away. And so these discoveries enable us to say that the encoding of the visual modality or additional modality is important for language models, enabling them to better grasp the meanings and the features of colors or shapes. And in conclusion, I would like to say a few words which summarize the whole work done. First, it is worth saying that the large language models indeed are very powerful architectures and tools which, being pre-trained on a simple target of language model, are capable of dealing with much more complex application problems without additional training. But alongside with that, it is interesting to understand that if we look inside these models, we will be able to see that each part within it is responsible for encoding its part of information, as well as the information that we as humans grasp: linguistic structure of the text, factology, time and space, and even visual concept. are generally being encoded inside the model that we are dealing with. And as a third takeaway, I still wanted to say that adding additional knowledge or training a model through other modalities helps us to better understand other notions related to these other modalities, like in the case of shapes and colors. And possibly this third point hints that text is not enough for a model to gain the whole knowledge in the world. It is possible to expand modalities, to add them once the language models are being trained, and possibly this would help us discover new forms of such models and move into the realm of smarter, bigger and better models that we're going to use in the future. So with that, let me finish my presentation. Thank you very much for your attention.